Okay, let's now try going, well, sort of backwards. How about this? Let's convert the uh, integral from 0 to 2 pi, integral from 0 to root 5, integral from 0 to root 5 minus r squared of r squared z cosine theta. Let's write that better. R squared times z times cosine theta dz dr d theta, which is currently written um, from the cylindrical coordinates to spherical coordinates instead. Okay, I think this is a good exercise. So we haven't been just described a shape. Sometimes, in fact, being described as shape, it can feel a little ambiguous. So instead, we've been given an integral. And so somebody else had, I guess, been given a shape and set up an integral. And now we need to take the information we see and pick apart and understand what shape was it. And then based on what shape it is, we should now then reset up the integral. So there's a lot of geometry. There's the task of taking the picture once understood and converting it into bounds for integrals. We're now doing that process backwards. So that's, I think, a very good exercise for us to be doing. So first of all, we see that z, the innermost integral goes from 0 to root 5 minus r squared. 5 minus r squared. The next integral r goes from 0 to root 5. And then the last outermost integral theta goes from 0 to 2 pi. And so we should try to understand what shape we're getting. And let's take a look at just the upper part here, right? So the upper value of z is given by z equals root 5 minus r squared. Of course, we have everything in between, but let's just understand what that upper part really looks like. Square both sides, and you have r squared is equal to 5, z squared is equal to 5 minus r squared. You can add r squared to both sides. So r squared plus z squared is equal to 5. Remember that r squared is really x squared plus y squared? So we've got that still plus z squared equals 5. This is a sphere, right? This is a sphere of radius root 5. And remember that r, it's the same coordinate. The r coordinate does not depend on the value of z at all, right? So r is just a distance in the xy plane only. So if you have a point where the z coordinate is non-zero, first you take that point, have it cast a shadow onto the xy plane, and look at the distance. So what's going on here? The sphere, this is the upper half, right? This is the upper hemisphere, or the northern hemisphere. Of radius 5, root 5. Of radius root 5. Now, that's what we get just staring at this now, right? Because of this equation here. The real question becomes, do we get the whole thing? Well, once you do that, you would, once you have your z bounds, you'd project down to understand, down into the xy plane to figure out what's going on. And if we now try to picture this information here in just the xy plane, well, r from 0 to root 5, so all directions because of the theta, this to me it's a filled in circle of radius root 5. And so this is the shape that's directly under, right? So you have the northern hemisphere of radius root 5. Directly under it is this filled in circle. So we actually get the entire, so what we're getting here, right? The point is that the region itself, the 3D region that we're integrating over, is a solid half sphere. And then which half? It's the upper half, I guess, right? The upper half meaning sort of the z greater than or equal to 0 half. Okay, so we have this integral up here. Let me just maybe copy paste it. Got this integral. Let's copy paste this down here. And now, based on this information here, we know what shape, right? We know that the region we're integrating over, geometrically described, is a solid half sphere and of radius root 5, and it's the half that is, yeah, maybe we'll include the radius here, of radius root 5, and which half? It's the half where the z-coordinate is not negative. Okay, but then what we need to do is let's reshuffle what's going on here and there, because I don't see here an r dz dr d theta. I just see dz dr d theta. So we need to organize this a little better. And the way I'd like to do this is the bounds of integration are exactly the same. Nothing's changing there. Okay, but what I'd like to do is shift one of those r's to be over here. So r dz dr d theta. And then we'll still have an r left and a z. You know what I'm going to do? Let's get the r next to the cosine theta. Why would I want to do that? Because that is x, right? And then what's left over is z. So the point of organizing it in this fashion is this part right there, that's the dv part, and then this part right here, that's the function. You know, that's f. And the point is, we know now from the fact that f is written as r cosine theta times z, it's really x times z. Okay, well, it doesn't really help us all that much that it's written as x. Well, yeah, let's go with it this way. So look, if f is written, so f of x comma y comma z written in rectangular coordinates is xz. But what we can do then is convert. Yeah, so let's convert f by rewriting x. You're gonna have to recall is rho times sine phi times cosine of theta. So that's x. Maybe I should also include this reminder that this part here, you're gonna have to go back and look. Rho sine phi, r is equal to rho sine phi. Maybe we'll just include the quick picture of how that looked, right? So there was like the positive z-axis, and you get to that point here, and there was this distance was r, this distance is rho. Maybe not thinking that because it's going to get messy. The angle here was phi, which because of the paraline here and there, this angle is also phi. The right angle there, I think I drew in there was a right angle here. In any case, the point is that from this picture, let's see, we've got opposite and hypotenuse. So from the picture, we have that sine of phi is equal to r over rho. So then you solve for r, and you have r is equal to rho sine phi. So that's the replacement that just occurred here. Okay, if you want to do it in, well, let's do, I'm thinking of two ways to do it. So, and then what about z? Z is still right here, right? So z, remember cosine of phi, or just stare at the picture, adjacent, z over hypotenuse rho. So z, we're seeing, is rho times cosine of phi. And so we can replace this z here, the next part there, you know, with rho cosine phi. Okay, so that's one way to do it. If you don't like that approach, let me try another way of saying all this. So I went from how this was written here, which was cylindrical, wrote it rectangular, and then converted that to spherical coordinates. If you don't like that way of writing f, I just thought of it, you could instead take the fact that f, as written up there, was r cosine theta times z, and then just directly convert. So the first of all, the r that's right here can, where does it, from over here, is equal to r sine phi. Yeah, sorry, rho sine phi. And then the cosine theta you can just keep because theta is a spherical coordinate. And then the z here is replaced just as we saw with rho cosine phi. So either way you do it, whether you go through thinking of rectangular coordinates, that f is xz, or you don't, either way, this is what f should be. So let me underline this in red, just like it was underlined in red over here. Okay, so there's that part. And then the dv part right here, the way that we're going to write that now is rho squared sine of phi d rho d theta d phi. Okay, I think we have all the pieces basically. What we need to do now is write equals integral sign, integral sign, integral sign. You don't actually need to leave a lot of space between the integrals. But then there's f in cylindrical coordinates. Here's now f either written like, well, these are actually the same. So we just copy one of those down. Yeah, so I'll just do the parentheses just for emphasis. Rho sine phi cosine theta. That part in the first set of parentheses is what x is. And then those are rho cosine phi. That's the part that z was. And then maybe I'll underline this red again just to keep some consistency of those parts. And then the part underlined green right here was dv, which in spherical coordinates looks like this. So we just really copy here rho squared sine phi d rho d theta d phi. And then we can place the bounds for the integral here. Well, first of all, rho. Remember the region, it's up here. Solid half sphere of radius root 5, so 0 to root 5. Then what about theta? Well, that's going to be 0 to 2 pi. So as far as the xy plane is concerned, we get all. And then what about phi, though? This is the upper half. So the angle created against the positive z-axis needs to be acute. So this should be a 0 to pi over 2 only instead of 0 to pi or something like that. So it's this pi over 2 part that's getting us the northern hemisphere.